This is lecture 27, and in this lecture we're going to talk about the concept of work and how it relates to energy. Now, work is, I think, one of the worst names for a concept in physics. When you hear the word work, you think of certain things, and what the concept of work means in physics is definitely different from any intuitive understanding you have of work. So think of this word, work, as some foreign word you've never seen before. This combination of letter W-O-R-K. You've never seen that before. You don't know what it means. Let's figure out what it means, right? Don't rely on any kind of intuition of whether you're doing work or not when you try to figure out if something is doing work in physics. It's a terrible name for a concept. Right, now that out of the way, well, what are we going to discuss? So, we're going to start by considering how forces cause changes in kinetic energy. And we're going to forget all about potential energy for now. We'll come back to that. We'll hook those concepts up at the end of the lecture. And part of this investigation brings us to this concept of work. We're going to define what it is. And crucially, we're going to state the work-energy theorem, and it's kind of the reason why this concept is a thing. And we'll go through some examples on the calculation. Now, we then go to what's called conservative forces. And again, we'll talk about what that means, and the idea relates back to work, right? So kind of building up the concept of work, and then we're defining a particular type of force in terms of work. Like a particular property that any the force can have. And it's this property that allows an interaction, a force, like gravity, say, right, to have a potential energy. So that's the logic of the lecture. And in the end, we might briefly ask, okay, well, what about forces that don't have this particular property that allows them to have a potential energy associated with them? What happens there? That's what we're going to do. And from my experience teaching this stuff, I know that work tends to cause a lot of difficulty, especially when you first meet it. So take your time with it, right? Take your time figuring it out. Work through the examples again, maybe watch them and then, pause the video, go back and try to work through the examples again yourself. Make sure you understand every step of the way. But the ultimate goal here is, well, twofold. One, justifying the notion of potential energy. Why does it work? No pun intended. And then also, well, how can I use work, this concept, to use energy in cases where there is no potential energy associated with a particular interaction that I have to take into account. Alright, let's get started on that. So, I want to figure out, what does a force do regarding kinetic energy? So here I mentioned I've got some kind of block, and this mass m that it has, and I'm pulling it with a string attached right here with some force F. So this force F, assuming there's no other forces to worry about, this force F is going to cause this thing to accelerate, right? You remember Newton's second law. Well, acceleration means change in velocity. That means change in kinetic energy, because kinetic energy is 1/2 mv squared. Let's just write it down as a reminder. So recall kinetic energy, I'm going to abbreviate it, is 1/2 mv squared. And so that implies that F causes a change in kinetic energy because it causes an acceleration, change in velocity. So what is that? What is the change in kinetic energy? Well, let's get there via a little trick. Let's start with something from a while back. Another recall also that I'm going to calculate the final velocity, some later time. Well, one way to do this using kinematics is I have the final velocity squared, the initial velocity squared, plus 2 times a times the displacement. Right? Remember that from kinematics. I'm going to write CF kinematics. CF, right, being a common abbreviation, means sort of compared to. Literally it comes from the Latin conferatur, to be compared with. So compare, your notes on kinematics. That's where we got this one from. It was just from understanding what acceleration is, and so on. So if I start with that, I can easily rearrange that. And what I'm going to do is I'm going to replace A by F over m using Newton's second law. So what I'm going to get is that the final velocity squared is the initial velocity squared plus 2 times F over m. So I'm assuming here there's only one force acting, that force F, so that is also the net force. And now I'm just going to divide this whole equation, like every part of it, by 2 and multiply by m. So just just by rearranging, we're going to get 1/2 mv final squared is 1/2 mv initial squared. So I'm dividing by 2, the half, and I multiply by m. That makes those go away, plus f dot dx. Alright, so now these terms look familiar, right? This is just the final kinetic energy, and final could mean at some later point in time than we started. Doesn't mean it has to be the very end of everything, but final of some time period that we're talking about. This would be the initial kinetic energy, and so the difference between them is given by the force times the displacement. And this force times displacement, this part here, we're going to call this the work. It is a name we give to this term. And what does this work do? Well, it is equal to the change in kinetic energy, right? Because final kinetic energy is initial plus, well, plus what? Well, by plus how much it has changed. So from there we right away see that the work is equal to the change in the kinetic energy. Before we move on from this idea, let's generalize this a little bit. So here I considered motion in just one direction, right? V final, V initial, there were no x and y components given, it was all just along a line. So what if I have more than one direction? Well, the total kinetic energy, right, is 1/2 mv squared. Now I can write this as 1/2 m vx squared plus vy squared, maybe plus vz squared or vz squared. Right? Why is that? Well, if this is the velocity v, how would I find its magnitude? This is its magnitude squared. Well, essentially by Pythagoras, the Pythagorean theorem, so it would be vx, vy, so v squared is vx squared plus vy squared. If in 3 dimensions, then you can do the same thing in 3D. And if you've never proved that before, that it also works in 3D, that vx plus vy squared plus vz squared is v. Sure, you can try it yourself. Just imagine it was a cube, and or like a doesn't have to have equal sides. And I want to figure out what's the length of this line from the corner down here to the corner up there. Kind of hard to draw on the page. And the way you could do this is you first find the length of a diagonal, a diagonal on the back side. That would be this length plus this length. And then you have this one triangle here between this diagonal and this one. You can find the length of this thing that goes diagonally through the cube, from down bottom left to far top right. And that's how you justify that the Pythagorean theorem extends to 3D. So if you haven't done it before, just think about this for a second. Okay, but now I can take it from here. That's 1/2 mvx squared plus 1/2 mvy squared plus 1/2 mvz squared. Okay, now each one of those is exactly what we had here, right? This equation works if I put a little x here, a little x here, a little ax here, or a little y y, the y velocity, the y acceleration, and delta y, and so on. Right? This equation holds for each component separately if the motion is in more than one dimension. And so then that means I can generalize this, my equation here, by essentially writing this 3 times. Once for x, once for y, sorry, once for x, 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 once for y, 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 and then z, z, z. Now this term is just going to give me the total kinetic energy, final initial, and here I'm going to have fx delta x plus fy delta y, fz delta z. Let me write this down. So I'm just going to say, by logic from above, but for each component, sort of like I do it for each component, this equation here, and then I add the equations. It gives me 1/2 mv final squared. It's my speed squared. Is 1/2 mv initial squared, the initial speed squared, not any single component, the whole thing, plus the x component of the force times the displacement in x, plus the y component of the force times the displacement in y, and if it's in 3 dimensions, then I'm going to have a third component, a z or z component, and a displacement in that direction. So this expression here is what's called the work energy theorem. Essentially it says the change in kinetic energy is this sum. So this would be the total work done in 3D. Now actually I can write this in a more compact form, and that compact form will look familiar to you if you've dealt with the vector dot product before. Namely, I can write this as f dot, as a vector dot, the x, where x is now, I'm going to call it ds, just the displacement as a vector. This is just a kind of a shorthand notation for this, where I have f, my f vector would be fx, fy, fz, and I use delta s for displacement. This would be delta x, delta y, delta z. So it's just a shorthand notation essentially for saying multiply this by this, add this times this, and this times this, and add them all up. Right, so this combining 2 vectors like this is called a vector dot product. It's extremely useful. It saves a lot of writing and has really interesting properties that allow us to do some calculations rather quickly that otherwise would take way longer. But I'm not going to, talk about all those properties right now. It's an important concept. We might come back to it. Right now, I just want to say this is kind of a shorthand to write the work done in 3D, but you can always spell it out in components like this. Let's write down what we mean by this work energy theorem, just so we have it on the page. I mentioned what it says, but let's write it down. It really says that the change in the kinetic energy, delta Ke, you write it in words too. So that's final kinetic energy minus initial kinetic energy. That is equal to the work done. Now, if I have more than one force, I would have to take the net force here, or equivalently, I calculate the work done by every force and then add that. Work done, put in parentheses, by all forces. Right, and so I could write this side as 1/2 mv final squared, and final always means, just at the end of some time period that I care about. It doesn't mean at the end of everything. Similarly, I doesn't mean at the beginning of of whatever's happening. It just means the beginning of the particular time interval I'm thinking about right now. And that's equal to F dot ds, the dot product of the force times displacement. Now I should put net force here, which we can write out in this form. Okay. So this is my work energy theorem. Let's put a big red box around it. Okay, that's fairly abstract. Let's look at some concrete examples. Here's my first example. Weightlifting. Here you are, and here's your heavy weight. So it's 90 kilograms. It's like 200 pounds. And sitting in front of you, and your goal is to lift it up. Right. So to do that, you have to do work. Well, what force do you have to apply on the weight? You need to apply a normal force that counteracts the weight of those weights, if you know what I mean. It counteracts the force of gravity on those bar weights. So you need to apply an upward force of, well, 900 newtons, right? Because it's m times g, and g is 10. That's just to balance out gravity, and then you can slowly lift it up. Well, technically, to make it go up, you have to apply like 901 newton, so it can start speeding up upwards, but once you're just lifting it at constant slow speed, you just have to balance out the weight. So you need to apply 900 newtons of force. To get from here to here, well, you have a force that's upwards, that is 900 newtons, and your displacement, let's call it delta, I don't know, it's called delta y, right? Upward direction, we like to call it y sometimes. 2 meters. That means the work done, the work you did, in the physics sense, would be 2 times 900, right? F times displacement, force times displacement, 900 times 2, 1800. Now Newton meters, Newton is a kilogram meter per second squared, times meter, kilogram meter squared per second squared. That's joules, the unit of energy, right? So work has the unit of energies. Remember, this is a kilogram meter per second squared, and kilogram meter squared per second squared, that's joule. 800 joules. Now, why is it that the given that you do that much work, why does this thing not have a whole lot of kinetic energy and is moving fast? Well, it's because something else did work too, namely gravity. But gravity also does work. In this case. Why is that? Well, gravity pulls down the whole way. mg. 900 newtons, right? The displacement, delta y, is still 2 meters. So, the work done by gravity, well, mg is 900 down, so it's minus 900. So, work done by gravity is going to be minus 900 newtons times 2 meters, which comes to minus 1800 joules. And so the total work done in this case would be 0, because you're doing 1800, gravity is doing minus 1800, negative work, totally a thing, right? You just have to force oppose the direction of motion. You get negative work. So total work done by all forces is 0. And so there is no change in kinetic energy. Right? If you wanted there to be a change in kinetic energy, like you want this thing to not just stop here, but fly up at 3 meters per second upwards, fly through the air, through your gym, and slam down on the floor, don't do it. But if you wanted to do it, right, you'd need to apply a bigger force than 900 Newton on the way up, so you're doing more work. Or in other words, you need to create a positive net force upwards as the weights are being moved up. There's kind of two ways to think about it in terms of how much work you do versus how much work gravity does, or by saying, well, if I have a bigger force than gravity, then there's net work up throughout this process. Now, what happens on the way down? Well, if you go, you lift up your weights, you lower them again. Well, if you lower them again, that just makes your delta y negative. So to change going from up here back to down here, all I have to do is put a minus in front of that. And I'm assuming you're lowering them slowly. You're not going to just drop them on the floor. You're lowering your weight slowly, so you still have to push up with 900 newtons, just very slowly, your hands go down. Well, in that case, you're going to be doing minus 1800 joules, because 900, your force is still up, because you're still supporting the weight, but the displacement would be negative. Put a minus sign there. But on the other hand, both this and this would be downwards. And so I've got minus 900 times minus 2, that's plus 1800. So going back down would just reverse the sign of the 2. Also means that if you go up and down, you lift your weight 100 times, well, I'm doing 1800 joules of work minus 1800, plus 1800, minus 1800, plus 1800, minus 800. So by the end of the day, when you've done this 100 times and you're thoroughly tired, well, you've actually done 0 work, which is rather silly. It's a silly thing to say, right? You've worked out hard, but you haven't done any work. Kind of one of those reasons why it's not really a good name for the concept. Here's another quick example that's kind of related. Let's suppose you're done lifting weights. So you pick up your bar, maybe you put it on your shoulders, maybe over your head, put it over your head, or maybe you carry it some other way, doesn't matter. You lift it up and you walk sideways back to put the weights back on the rack. So you're doing this. Are you doing work? Well, you're applying a force, right? You're pushing up with 900 newtons just to support the weight. The weight wants to come down. Gravity is pulling it down with 900 newtons. So for it to not fall down, you have to support it with 900 newtons, just as before. But my displacement is in this direction, delta x, right, to the right. So I have to think about directions here. My total work done by me, what is it? Well, it's going to be the x component of the force times delta x, plus the y component of the force times delta y, plus the z component, never mind, we're in 2 dimensions, don't have to include that. Well, I'm pushing upwards. Let's make this my y direction. Let me label this. Let me put a coordinate system into the picture. Y is up, x is right. Well, I'm pushing up, so this is 900 newtons. Not pushing forward. Delta x, maybe, let's pretend you have to walk 10 meters. Well, then this makes this one here 10 meters. But what about the others? Well, my force is upwards. There's no force I'm acting to the right. So this here is 0. Similarly, the bar is moving sideways. It's not moving up or down. So this is 0. So 0 times 10 plus 900 times 0, well, that's just 0 work done, 0 joules. So you're not doing any work if you're holding this above your head, moving sideways. And again, that makes sense from what we know from before. If you act a force that's perpendicular to the direction of motion, you're never going to cause the object to accelerate. At best, if there was a net force up, if gravity wasn't pulling down, well, that would cause the bar to change direction. Right? Remember, turning motion. Having a force or an acceleration perpendicular to the direction of motion does not make the object speed up or slow down. So again, this is consistent with what we've learned so far. Similarly, gravity is acting down. Well, gravity, you could just put a 9 minus 900 here, but again, the work done by gravity in this process is 0. So it's somewhat counterintuitive, right? You feel tired after carrying this bar 10 meters, 100 meters, 3 miles, right? Walk like that for 3 miles, you're going to be tired. But you've done no work at all, according to our definition of work. Here's the next example. Imagine you're pulling a sled. And you're pulling it with a rope, and the rope is like this. So you're walking in front of the sled, some over here, and you're pulling it with a tension of 30 newtons. So it's not super heavy, or at least doesn't, it's fairly easy to pull along. The snow is nice and frictionless, so almost frictionless. So we're going to calculate this twice, once without friction, once we're including a little bit of friction. Now, of course, you could solve this problem using forces and kinematics, right? We want to find the speed of this thing after it's traveled 100 meters. So how you might have done this in the past, and you might still do it, is that you find the net force to the right, and then you figure out what's the acceleration using Newton's second law, and then you know the acceleration, you can use kinematics to figure out how fast you're going after 100 meters. Well, we want to figure it out using the concept of work. Now imagine this angle between the direction of the rope and the horizontal is 36.7. That's a weird number, you say. Why did I pick this? Well, it's kind of a remarkably nice number in that the sine of 36.7 degrees is 0.6 and the cosine of 36.7 degrees is 0.8. So it kind of has nice round sines and cosines, I suppose. Just to keep the numbers simpler. Alright, let's figure out the work done by the tension. Well, what is it? Let me write it as W subscript T, work done by tension. Well, it's going to be that, not F, the tension, the X component of the tension, times the displacement in the X direction, plus the Y component of the tension, times the displacement in the Y direction. I haven't actually defined X and Y. It could be some kind of funny angle. It turns out that this expression, this sum, right, is going to be exactly the same no matter how you choose your coordinate axes, which is not obvious. This is kind of where this dot product idea comes in, and we can talk about it more in class, so maybe you've seen it in one of your math courses. But let me make the obvious choice, because we're going to the right. Let's call this X, let's call this Y. Okay, so what are my components, right? 30 newtons is the tension, but the tension is at an angle. Well, this is going to be 30 newtons times cosine of 36.7 degrees, because it's the adjacent, that gives me the horizontal component, times what's delta x? Delta x is 100 meters, because we're traveling to the right. And I'm going to add to that the vertical component, that is 30 newtons, that's the tension, times the sine of 36.7 degrees, and then what's my displacement in the y direction? Oh, it's 0. It's flat ground. At least that's our assumption here. Right, so actually this part here drops out completely, and I only get 30 newtons times cosine 36.7. We wrote it up here. 0.8 times 100 meters. What does it come to? If I'm not mistaken, or plus 0. That comes to 30 times 80, that is 2,400 joules. So that is the total work done, and if there's no friction, then that's the only force. Well, you say, what about the weight? What about the normal force from the snow? True, they're there, but notice that they're perpendicular to the direction of motion, which means they don't share any components. It's a bit like the example of the walking with sideways with those weights, right? Gravity pulls down, displacement is to the right, they're at right angles, no work is gonna be done by that force. Same for the normal force. Normal force points up, but the direction of motion is right, and so the normal force is not doing any work because it has a y component, no x component, and the displacement has an x component but no y component. So this thing, for normal forces of tension, would just come to 0. If it was too fast for you, just pause the video and try to figure it out yourself. Okay, so we found the total work done. And now I want to figure out, well, what speed does that net me? right? But how fast is this thing going? That was the question. Well, this is equal to our change in kinetic energy. How do I know that? Oh, that was this work energy theorem we wrote down a little bit ago. So that means my final kinetic energy, let's write it out in the words, final kinetic energy minus initial kinetic energy, right? The difference between them, that is the change, is equal to 2,400 joules. But my initial one is 0 because we start at rest. So that means I have just 1/2 mv final squared is equal to 2,400 joules. And now mass is 50 kilograms. That was given as part of the question. Let's have a look up here. 50 kilograms, that's what it says. So let's figure this out. So I'm going to get V final squared is 2 times 2,400 divided by 50. So that's this divided by 50, which comes to 96. And so we just squeeze in here. Vf is the square root of 96. Now, what is this? It's probably something like 9.8 meters per second. But nothing to do with gravity, just coincidentally the same digits. Square root of 96 around 9.8. So I hope that made sense, right? We worked out a change in kinetic energy by working out the work. And then we used, what you know about initial kinetic energy to solve this for the final velocity. Okay, let's repeat that problem one more time, but this time we're going to add friction. We're going to assume there's 10 newtons of friction. Right, so that's our new part. So this was part A. Let's do part B. So now have 10 newtons of, it's going to be kinetic friction because the thing is moving. Right? So we already know the work done due to the tension. That doesn't change. Assuming I'm still pulling with the same 30 newtons as before. The work done by tension is still equal to 2,400 joules. No change there. But now I also have work done by friction. Right? And what's that equal to? Well, it's the force of friction, F. I guess friction, let me write out like this. Friction subscript x times delta x plus friction subscript y times delta y. That is my work done by friction. Right? Now friction is 10 newtons, but it's backwards. So it's minus 10 newtons times 100 meters. This was in a negative x direction. If the sled goes right, friction is left. Plus 0 times 0. Okay, I can really forget about motion in the up-down direction. So that is minus 1,000 joules. So that means the total work done, the net work done, follows, right? Net work done is 2,400 joules minus 1,000 joules, which comes to 1,400 joules. And now I proceed from there just as before. That's equal to 1/2 mv final squared. Well, minus 1/2 mv initial squared. That's the work energy theorem, but this is just 0 because we start from rest. So we can solve this. When I get that v final squared is 2 times 1,400 joules divided by the mass. I'm just rearranging this equal to this, divided by 50 kilograms. Now, what does that come to? If I'm not mistaken, that will come to 56 meters squared per second squared. Then we need to take the square root to find the velocity. V final is the square root of 56, which is about 7.5, I'm gonna say, meters per second. Pretty close to it. Okay, so significantly slower than before. We found that at the end of this run we're going 9.8 meters per second. So friction makes a difference. Of course, we could also have worked this problem out differently by finding the net force, then just figure out the work done due to the net force. That is the net work. Now, let's imagine I have a box, and the box starts up here and it ends up down there. So this is higher up than this. It's delta H, some height difference, and also some displacement sideways, delta L, I guess, for length. So it goes from here down to here. What's the work done by gravity? Now, at the face of it, you can't calculate that because you're not told what the path is. You don't know what the displacement is. Am I going this way? Am I going this way? You could maybe assume it's going in a straight line, but you're not told otherwise. Well, that seems a bit fishy. So let's figure it out. Figure out the different possibilities. Right? Let's suppose I'm going to follow the following path. Let's suppose we let this box drop down. Or there might be other forces involved in this, right? Otherwise it'll just fall and stay there. There must be some other force acting, but I don't care about those right now. Just want to know what's the work done by gravity. Well, along this path it's going to be, well, the weight is down and the displacement is delta H. So it's mg times delta H. Okay. Now what about here? Well, here along this path the weight is down, but the displacement is sideways. So that means the work done is 0. Right? Let me write out y. It's F x times delta x plus Fy times delta y. Now, this is delta L, but this one is 0 because gravity acts down, and this one is 0 because there's no displacement up or down along this path that happened over here. And so overall this thing is 0. Right? Again, think of the person with the weights walking sideways. Okay, let's go a different path. So the overall, the total, right? So let's write on green path. The work done is mg times the change in height. The work done by gravity. I only care about gravity right now. Let's go a different path. Let's say we're going to go first across and then we're going down. Well, again, the work done along here is 0. Why? Because gravity acts down. It has a y component, no x component. But the displacement is sideways. It has an x component, but no y component, so the exact opposite. So again, you're in a situation where one is 0 in the first term, the other one 0 in the second term. No work gets done. What about here? Well, here the force is downwards mg. The displacement is downwards delta h. Same direction. So I'm going to get mg times delta h. Okay, so the blue path, the work done is again mg times delta h. Let's pick one more path. How about we go, I mean, one path you could pick is like you go down halfway and across and then down maybe. Let's do it. Because I want to go horizontally across, although it doesn't ultimately matter. Well, if I go halfway down, then this is going to be mg times delta h over 2, because I've got only half the displacement. Along here it's 0 again, same reason as before. Then here I've got another mg delta h over 2. So what's the total? The red path, the work done, is going to be twice mg times delta H over 2. Again, that's the same thing as before. Just this. Not sure why I wrote it so high up. Bring it down a bit. mg delta H. Same as before. Now you could pick another path too. You could say, well, I want to do something crazy and I want to go like up first, and then across, and then down. But going up, gravity will be doing negative work to compensate the extra work it does over here. And again, you're going to end up with the same result. You could also try a sort of diagonal path, right? I mean, you could try any kind of path, but let's go with the diagonal one. Well, what do we get there? Well, think about this carefully. There's a displacement horizontally and a displacement vertically. Meanwhile, the force of gravity is just vertical. So the purple path makes the work done. Let's write it out. Fx times delta x plus Fy times delta y. And again, I'm using x as horizontal, y is vertically up. This is before. Well, the force in the x direction is 0. The change in the x displacement is delta L. That's the distance I'm traveling. When I add to that, the force is minus mg, at least if the y-axis points up. The displacement is minus delta H. And really I could have had minus, 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 but the minus is always going to cancel out. You can see right away it's going to end up the same thing once again. And indeed, you could split up your path in any kind of funny shape. You're going to end up with the same result. Right, we haven't proved it, but hopefully you can see how that always works out to be the same. So the work done is path independent. And notice what the work is, mg times the change in height. That's just a change in potential energy, if you remember mgh. Let's summarize those insights. First, really a definition. An interaction, or a force, is called conservative if and only if the work done by this force is path independent. The example we just saw was gravity. No matter what path we took, gravity did the same amount of work. Then, if a force is conservative, that means if the work done is path independent, we can come up with an associated potential energy expression. What is this potential energy that we can write down? Well, the difference in the potential energy between 2 points, say our start and end point of that box, that difference is the work that the force would potentially do going between those points. Okay, let me show you what I mean by that, right? We start here, we end here. What is the potential energy difference between being up here and being down here? Well, I can calculate it by calculating the work done as I go from here to here. The work done specifically by that force, by gravity, right? So if I go from a high point to a low point, then gravity will do this much work. And so the difference in potential energy between the high point and the low point is exactly this expression. Why? Because I don't have to know about the path. So I can just say, hey, at this point, the potential work done by gravity is going to be mg times delta H. Notice, of course, that as I go down, I technically have a negative change in potential energy. It's becoming less. The potential energy is going down, but the work then is positive. There's kind of this opposite of science. If you actually want to work it out, you end up with a minus sign. You don't know where it came from. Well, it came from the fact that higher potential energy means that more work could potentially get done when you go back down. So this minus sign sneaks in. It's usually fairly obvious, as long as you have a clear conceptual understanding of what it is that you're doing. Okay. Now, there's a difference in potential energy, but so far we haven't really talked about like just differences. We had the potential energy. Well, what we had to do in all the potential energy problems, say from the last video, is that we had to define some kind of reference point, some zero height. And that is essentially arbitrary, but often there are easier choices and harder choices, or useful choices. Right? Let's write this down. The potential energy itself is just the difference of potential energy the difference between the current point you're at. I say here this point has 6 joules of potential energy, while it's 6 joules more than some freely chosen reference point. Energy between, I'm going to call it the point of interest, at this point right here. What's the potential energy? And a freely chosen reference point. Now there are conventions. With gravitational potential energy, the way we've met it so far, really you can pick the ground or something, but it's really a very free choice there. It doesn't matter. Some other examples we're going to meet. There is a fairly established choice. For example, we talk about the gravity between planets, Newton's theory of gravity, then the reference point of zero potential energy is when two objects are infinitely far apart. Or with a spring, right? A spring, zero potential energy in a spring, well, that is when the spring is at its equilibrium point, at its rest position, and it's neither squished nor stretched. But in all those cases, you really can just define your potential energy zero any way you want, only ever differences matter. And if you can use potential energy, if you have a conservative force, then I'd strongly recommend you use potential energy. It's most likely way easier to deal with than dealing with the concept of work and calculating the work. Okay, one question then remains. The question is, well, what forces are conservative and what are not? Are there any forces that are not conservative? Well, let's define a term for them. A force or interaction, that same thing, is called non-conservative if and only it is not conservative. Right? It sounds almost silly, but ask a mathematician about open and closed sets and whether they're opposites. It's not always as obvious as it seems, so we're going to do this rigorously, and we're going to talk about non-conservative forces being any force that is not conservative. Can we come up with an example? Yes. And one very, very important example is friction. Right, so let's imagine I'm looking down on a table. This is my table. And I'm looking at it from above. Right, and I imagine I put my textbook here. And I can move my textbook from this corner to this corner. Maybe that's some distance, let's say 2 meters. Let's suppose kinetic friction, remember that just depends on the normal force, in this case that's equal to the weight of the book, and the coefficient is 1 Newton. Let's just suppose, for example, we're then going along the green path, the work done by friction is going to be minus 2 newtons. Why is it minus 2? Because displacement is 2 to the right, 2 this way, but the force of friction, of course, opposes the motion. It's going the other way. Meanwhile, if I took the book and I moved it up this way, and maybe that is 1 meter, could be anything, then I move it across. Then I move it back down. Well, what is the work done? Going from here to here, right? The displacement is 1 meter, but the force of friction opposes the motion, so it's back down. The work done here is minus 1 joules. I should have written joules down there. Goodness gracious me. Newtons is a force. If you were confused, good on you. It means you were paying attention. Then going from here to here, displacement is to the right, but friction opposes the direction of motion, so it's to the left. So the work done along here is minus 2 joules. Now we're going to go from here down to here, and you might say, well, does this cancel out this motion up here? No, it doesn't, because the displacement is down, but the friction is up, as seen on the page. Of course, this is all horizontal. We're looking downwards onto a table. So again, the work done here is going to be minus 1 joule, right? Displacement this way, but then the force of friction this way, opposing each other. Negative work gets done. So the total, in this case, is minus 4 joules, and only minus 2 joules here. Not a conservative force. And that means I can't write down the potential energy, because I can't say the work that gets potentially done going from here to here, because it depends on what path I take. If I go, in some funny path like this, a certain amount of work is going to get done, and it's always going to be negative because friction always opposes the direction of motion. And in that case, friction, well, it's annoying. I can't write down the potential energy. If friction affects my system and I want to deal with energy, we have to stick with calculating the work. Spelled this out here. When dealing with non-conservative forces, in the context of energy, we have to stick with using the concept of work. We can't switch to using potential energy. Potential energy is nice and easy, right? You saw it in the last video. Super useful. Well, if you've got friction or air resistance, or maybe something like a thrust of a rocket, where the direction depends on which way the rocket is pointing, in those cases, non-conservative forces, you'll have to deal with work. Now, in many cases, the work done by non-conservative forces is negative, like friction, air drag. They always oppose the motion, but that's not generally true, right? It's not always true, because the example of rocket thrust, for example, where the direction of the force depends on which way the rocket is pointing, so it's in no way guaranteed that the work done is path independent. Well, it's not always the same, right? But in the cases, finish my sentence, in the cases where the work done is negative, no matter what, it's a non-conservative force. So we always lose energy. We call those dissipative forces, because they dissipate energy. So here I'm stating this. A non-conservative force is dissipative if it only ever does negative work. Sort of. This is not a proper definition. This is a bit sort of a vague intuition. Because remember, friction can do positive work. For example, if you drop a suitcase onto a conveyor belt at the airport, the conveyor belt is using friction to make the suitcase go. Right. So there are sort of counter examples. Although at the same time the suitcase is slowing down the conveyor belt. In any case, the primary examples are friction and air drag. Maybe I should write it down too. The actual definition is slightly more complicated, but I think what I wrote down gives you a good feel for it. The types of forces I mean. Friction and air drag, or water, any fluid drag. So where does this energy go? The kinetic energy becomes lower because of, say, air drag, right? Something moves through the air, rocket falls in from space, goes back into the atmosphere, it's slowing down a lot. Where's the energy going? Well, if you ever watched a rocket fall down and seen pictures, you know the rocket starts to glow, hot, red hot, white hot even. Heat is produced. And if you just take your hands, right, and you rub them together, they warm up. Friction creates heat, creates thermal energy, to be more specific. So let's write this down. The lost energy is now thermal energy. So it's no longer mechanical energy. It's no longer kinetic or potential, except in the sense that thermal energy is the kinetic energy of individual atoms added up. But it's kind of lost to our motion, we can't just easily get it back. You can get it back in certain contexts. You can turn thermal energy into kinetic energy if you have what's called a heat engine, but that's the subject of a different lecture that is not in this course. Point is, there's friction, kinetic energy is lost while thermal energy is created, stuff gets warm. And it could be very little, right? You might not notice it, but it would, if you could measure temperature arbitrarily, accurately, arbitrarily precisely, then you could always detect that if there is a dissipative force, air drag, or friction, thermal energy is created as kinetic energy is lost. Now, there was a lot of material in this lecture, a lot of this kind of abstract, so take your time with it, but I think a lot of these concepts will make more sense once we start looking at some more detailed examples, which is what we're going to do over the next couple of lectures. I'll see you there.